Good morning, everyone. Thanks for coming to the talk. So, if you look at the program, the talk is actually called Announcing Broadway. But I figure out that instead of just talking about Broadway and how to use it, which you can actually do by checking out the documentation, I thought that I would tell the story about the road that led us to Broadway. And the reason why I think this is an interesting story is because it has been going on for about 6, 7 years. And we did not know when we started on this journey, when we started on this road, that eventually it would lead to Broadway. And we're not even sure if Broadway is like the last stop in this journey or not. So we'll talk about all those things. But before we get to tell this story, what I want to do is to do a very quick introduction to Broadway to see if you can get interested on the topic, and then we can tell this story. All right. So what is Broadway? Broadway is a new library for concurrent and multi-stage data ingestion and data processing with Elixir, right? So what is the problem, right, that Broadway tries to solve? So imagine you are doing this. You are storing data in a queue system like Amazon SQS, Google Cloud PubSub, and you want to get the data, or RabbitMQ, Apache Kafka, whatever, and you want to get the data out of the system and process it concurrently as efficiently as possible, efficient in terms of time and in terms of cost. And that's what Broadway allows you to do. So you can get the data out of the systems. You're going to set up a bunch of processes, a bunch of entities to compute and work with this data concurrently. And one of the things that you may also want to do, which is step 3, is to batch this data, right? So maybe after you process this data, you want to batch it to maybe send a batch of data to S3, or maybe you actually want to acknowledge this data. So for example, if you're using SQS, one of the things that you have to do is that you need to tell SQS that the data was processed. And the cheapest way of doing that, and the most efficient way of doing that in terms of time as well, is to create a batch and acknowledge the whole batch to SQS. So you want to batch the data from time to time so you can publish it, write it elsewhere, or you want to acknowledge it or acknowledge it. And with Broadway, you can do all of this in like 20 lines of code, okay? And this is how you use Broadway. So Broadway is a library written in Elixir. Here's some Elixir code. So you define a module. I hope you can see it, but there's not a lot of detail in there. So you're going to define a module, and you're going to say, I want to use Broadway, right? And then after you do that, you have to implement just 3 functions. One is a start link, which is going to start your Broadway pipeline. We are going to look at it. And then after you do that, you're ready to write your business code, your domain logic. After you do that, you have to implement 2 other functions. Handle message, which is going to be invoked for each message, for each event, and handle batch, which is invoked every time you build a batch. So handle message and handle batch is your code, right? You do what you want in there, what you have to do. And on start link, what you do is that you define your pipeline. And how does define this pipeline looks like? You just call this function called Broadway start link, and you pass your configuration. You're going to say something like, look, I'm going to have a default producer, and what this producer has to do is to get data out of SQS, right? And then you pass the queue name, and then you're going to say, I want to have like 4 producers. I want to have 4 things connected to SQS and getting data. All right, and then you say, and I want to process this data, so I'm going to have a layer of processors, and I want to have 20 processors. I want to have 20 processes that are going to be working on those messages that are coming from SQS. And then after you process this data, you want to build a batch. And you have 2 parameters to control your batches. So one is the batch size. So every time you get up to the batch size, you say, okay, my batch is done. But if you cannot get up to the batch size in a period of time, in a timeout, we are going to emit the batch with how many elements it has in it. So we have, in this example, I'm using like a batch size of 10 and a batch timeout of 1.5 seconds. So if I cannot get 10 elements in a batch in 1.5 seconds, I'm going to send that batch as is. So you can do the handle batch and process the batch in any way you want. And that's it, right? This is all you have to do. Everything else is your code. Okay, and when you do that, we're going to set up a pipeline that is going to process your events concurrently with back pressure. We provide grace shutdown, and we have many other features planned down the road. All right. But in order to get to this point where we can have Broadway, there was, as I said, a very long journey. And that's the topic of the talk for today. So on our schedule, I want to talk about three separate things: collections, GenStage, and Broadway. But before I get to that, let me just ask some quick questions just to see, quick show of hands. So who here is familiar with Elixir, has used Elixir? All right, great. And who here knows about GenStage or has used GenStage? Fantastic. Has somebody already used Broadway? We released like 2 days ago. Fantastic, thank you. All right, so let's get started. Collections, right? So when I started Elixir, it was in 2011, and it started as a fun project. I like to say that nobody, when they have a problem, they say, I know I'm going to solve this problem. I'm going to create a new programming language, right? Because congratulations, now you have 10,001 problem, right? So it started as a fun project, and basically what I wanted to do is that I wanted to learn how programming languages work. I don't have a formal computer science background, so I wanted to study, learn more about that. And at the time, I was already using the ERLANG virtual machine for a couple of things, really enjoying it. And I was like, well, I might as well write one for the ERLANG virtual machine. So I built like this project for fun that was really broken and bad in many different ways, and it lasted like 3 to 4 months. But some time after that, there was like this thought in the back of my head, like, well, maybe there's something here. Maybe there is an opportunity to have a programming language that runs on top of the ERLANG virtual machine that offers a couple different things and a couple different perspectives. And some of those perspectives, people talk a lot, like, oh, you can do metaprogramming with Elixir. Cool, right? But the other perspective is that which perhaps more important, is that we wanted Elixir to have a really strong focus on data types. And there is one class of data types that we use a lot every day, which are collections, right? So we're talking about lists, ranges, sets, dictionaries, queues, and so on. And we wanted to have a very good support for collection, but perhaps, again, most importantly, is that we wanted to have a unified approach for collections. There are a bunch of different things you can do with collections, but we wanted to have a unified view and approach to all of this. So with time, we built a list of requirements of how we want collections to behave in Elixir, right? So one of the things that we wanted to have is that we want collections to be polymorphic. And what we mean by this is that if we have like 20 different collections, we did not want to have like 20 different APIs to work with each of those collections, to traverse those collections. We want to have one API that can work with all of them, that can accept many different shapes, hence polymorphism. But we also want this polymorphism to be open, to be extensible. What we mean by this is that imagine that Elixir ships with like 10 types of collections. Our API, this polymorphic API that we provide that works with all collections, should work with the collections that are part of Elixir, but it should also work with any collection that any Elixir developer may write in the future. So if you write your own collection data type, like a special kind of tree or anything else, you can just tell Elixir, like, hey, you can teach Elixir how to traverse that collection as well. And we also want it to be general. We want our collections to work for things that are in memory, like a list, a set, or a queue, but it should also work for resources. So for example, if the data that you want to traverse is in a CSV file, for example, we should be able to use the same API to work with that collection too. Or the database, it doesn't matter, right? It should work with resources. And working with resources means that we should be, when you iterate or when you traverse the collection, you're going to take care of opening the file, traversing it and closing it at the end, and everything related to the resource management, so you don't have to do it by hand. And finally, we want it to be, in lack of a better word, we want it to be, oops, 2 clicks. We want it to be tunable, okay? And by tunable, I mean Elixir is a strict, eager language, and we're going to talk about it soon. And I want it to make it relatively easy so you can have a collection and you can work with it eagerly, but if you want to make it lazy and work with it lazily, you could do that too. And then maybe even concurrent and distributed in the future. And we're able to implement almost all of those features thanks to an abstraction that we wrote about it. So I'm not going to the technical details here. I wrote a blog post some time ago called Introducing Reduces with 2 E's. You can check that out later if you want to more about the details. But Reduces is an implementation of the iterative library that we have in Haskell adapted to Elixir. We could not use iterities from Haskell as is. It would be not very efficient in the ERLANG virtual machine. We did a couple of changes. Those changes led to reduces, and that's how we were able to get a bunch of those features. We were able to solve a bunch of those requirements. So let's take a look at them from the developer perspective very quickly. So in Elixir, when you're going to work with collections, you use the enum module. And here, so for example, we can see we are using a map that allows you to map over the elements of a collection. And you can see that here it's polymorphic because sometimes I'm passing a list as first argument, but I can pass a range as well, and it just works. Okay? And it's also extensible because the enum module behind the scenes in Elixir uses the enumerable protocol. And a protocol is something that you can implement at any time you want for any data type. So if you have like your own data type, imagine that you implement a red-black tree or something like that. You can just implement the enumerable protocol for it, and Elixir will be able, and you'll be able to teach Elixir how to enumerate that data type, that collection. So you can do that at any moment for any data type, and you just have to implement 4 different functions: count, member, reduce, and slice. Our collections, they're also general. So here, for example, if I have a list of strings, okay, I can I say, hey, I want to representing possibly like a list of lines. I can go and upcase all of the tasks that is in each line. But if those lines, they're coming from a file, again, you can use the same API. You don't have to worry about it. So I can say, hey, actually, everything that I want to upcase, right, to convert to uppercase, it's coming from a file, right? And then you just say, look, this is the file that I want you to traverse. And when you traverse that collection, we're going to do everything. We're going to open the file, get line by line, right, and then close the file at the end. And we're also able to make collections tunable up to a certain extent, okay? So let's see how that works. So collections in Elixir, they are eager by default. So imagine this piece of code. I have a collection with 1, 2, 3, and then I call enum map, passing a print function. And what this print function does is that it prints the value that it receives and returns the value itself. Okay, so we call enum map, printing each element of the collection returns themselves, and then we call enum map again, printing each element in the collection and then return themselves again. So you can see that this is going to print 1, 2, 3, 1, 2, 3, and then return the whole list, the whole collection as 1, 2, 3, right? And the way it works, because it's eager, when you call enum map, at that moment, we traverse the whole collection and we print each element and we build a new collection. Okay, this is important. We're going to build a new collection after the first enum map operation. And then in the second enum map operation, we're going to do the same thing. We're going to print each element, and then we're going to return yet another new collection. Right? So every time we do that, we are traversing everything and building a new collection. Luckily, we can make everything lazy by doing one change. We just replace enum by string. And when we do this change, you can see that the result already changes, right? We are no longer executing anything. We're just returning a string. That's because the string is lazy. When you call a string map, nothing happens. It just stores the computation. So a string, you think that it's a recipe, okay, of everything that you should do with a collection. So for you to execute the string, you need to do something eager. You need to, for example, say, I want to run this string, or you want to say, I want to convert this string to a list. So when we do that, for example, by calling enum to list, you can see that now it executes, but it prints 1, 1, 2, 2, and 3, 3. It's no longer 1, 2, 3, 1, 2, 3, right? It's 1, 1, 2, 2, 3, 3. And the reason why it works like that is because the string, it fuses all of the computations into one. So you no longer have to traverse the collection multiple times. So what the stream does is that you are going to express all of your computations, and when you execute the stream, we are going to fuse those computations and traverse the collection just once. So we are going to get 1, and we go through all the operations, 2, go through all the operations, and so on and so on. And this is extremely powerful because, for example, now we can work with really large collections, right? If you have a 1 gigabyte CSV file on disk, in the previous way, we would get this whole file, load into memory, and traverse it multiple times. It would generate tons of garbage. But now, because we can fuse everything, we traverse line by line, right? We have to load the whole file into memory, right? So it allows us to work with large collections. It allows us to work with potentially like infinite collections because you're never loading everything into memory. And it was exactly this feature set that we shipped as part of Elixir 1.0 back in 2014. So when we look at our requirements, we're able to get really far in our list of requirements, right? We're able to make them polymorphic, extensible, they are general, and we're able to make it easily so you can go from eager to lazy. And after Elixir 1.0 was out, we took some time to rest, but shortly after, we decided to try the next step. What if we can now make it go from lazy to concurrent, okay? And the first thing that we tried to do was actually quite inspired by reactive extensions from .NET. And here's the first thing that we tried. So imagine that we have like this complex pipeline. Imagine that you are getting a file, can be a CSV file, and then, so you're getting a file, and then you are mapping. So consider each arrow with the 3 dots to be an operation. Then we map, then we filter, then we do this, and then we do that, right? So we do a couple different things. We run this stream at the end. So our first approach was, what if we have like a stream async operation? And every time you call stream async, it says that all the computations before that happen in a separate process. So that was our first attempt, right? So imagine here, if we have this pipeline, when we call stream async 3 times, what is going to happen is that we are going to have one process, so one entity of computation, right? Like get the data from a file, and that is going to send to the other process that may map over it, another process that is going to filter, and then we have like this pipeline. It happens that this is a very bad idea, right, for a couple different reasons. So the first one is that it is error prone, right? Because for this to work, we are telling the developer to go and put the stream async in the proper places, right? And so we're basically telling the developer, like, you can go and optimize the code in whatever way you want, but usually our intuition on how code should be optimized is not usually, not 100% correct, right? So it's very manual. So this is already not good, right? And maybe we're going to get some characteristics in our development machine and different characteristics in production, not great. The other thing is that this is centered around moving data, right? We are moving data around. And the way we model this in Elixir, right, all those entity of computations, it's processes. And those processes, they communicate by sending messages, right? So, and when we send messages in Elixir between those entities that are running concurrently, the data has to be copied, right? So this is not good because we can potentially be generating a lot of garbage, again, by copying the data between processes. So ideally, we don't want to move the data a lot. We want to move the data between processes only if we have to, right? It's better usually to move the computations around and be able to send computations between things because they are super cheap to do that. They are references to things in your memory, but not the data, right? And perhaps most importantly is that when we started to look at this from the point of view of processes, right? So when we call a stream async, we create a bunch of different processes. When we create processes in Elixir or in ERLANG, usually the question that we ask ourselves is, okay, I'm creating a bunch of separate processes, right? Then eventually we end up asking ourselves, well, what is going to happen then if any of those processes crash, right? I have a pipeline of things running concurrently, and imagine that one of those things go wrong. What is going to happen with the rest of the system? And this is particularly the part where I think that writing software for the ERLANG virtual machine made me a better developer, because before, the José in the past would probably write stream async and be very happy that it works and never worry about the failure semantics. And the model in ERLANG helps us really think about that, right? And not only about fault tolerance, because again, we're sending messages between processes, and those messages go to a message queue that is unbounded. What happens if there is one step in your pipeline that is really, really slow, right? And then you have a bunch of things sending data to it, and that process can't keep up. Eventually, you can run out of memory, right? So you also have to think, wait, what about back pressure, right? What is going to happen if I'm sending too much data and there is something that can't keep up? That thing that can't keep up needs a way to communicate somehow that it can't keep up, right? We need to have some kind of control in here. So when this question showed up, it made it clear to us that we were approaching the problem from the wrong angle, right? We were trying to approach this problem from the perspective of streams because that's how we have done things so far. But it was clear at this point that we had to try something else. We have to try to approach this problem from the perspective of processes. And what this means is that, in ERLANG and Elixir, you have a bunch of different process-based behaviors. So for example, we have something like a Gen server, which is used to model client-server interactions. We have Gen event, which is about events. We have Gen state M, which is about state machines. So we were thinking, well, we probably need a new process-based behavior, something that is about those computations and back pressure and exchanging data. And we did build 2 or 3 different prototypes explored, and those prototypes, each of them got different names. So we had like Gen router, Gen broker, but the one that actually worked and we're really happy with was called GenStage. Okay. So that's the first part of the talk, right? And just to kind of tell a little bit how we have always focused on having really good tools for working with collections in Elixir and how we wanted to work with this unified approach. But at some point, this unified approach kind of was not enough. We had to tackle things from a different angle. And this different angle is GenStage. So what is GenStage? Okay, GenStage is a new behavior, right? So it's a new process-based behavior. And the goal of GenStage is to exchange data between processes, right? Transparently and with back pressure. So the goal is that you get features like back pressure and the exchange of data transparently. You don't have to worry about it. We are going to take care of it for you, okay? And we have 3 kinds of stages. We have producers, we have consumers, and then we have producers, consumers that they are in the middle. So a GenStage pipeline can look like this. So we're going to have a producer. So for now, it looks very similar to what we were trying to do, right? So we can have a producer, we can have, and then it sends data to a producer consumer, potentially to another producer consumer, and so on, until it gets to a consumer at the end, right? So the producer is the source, the consumer is the sink. And the way that GenStage works is that it is demand-driven. So a stage cannot just send data to a stage downstream. That's not how it works. The way it works is that the first thing that should happen is that the consumer subscribes to the producer. That's the first thing that happens, okay? And then after the consumer subscribes to a producer, the consumer can send demand. The consumer can say, hey, give me 10 elements, give me 10 messages, 10 events, whatever. And then only after the producer receives that demand is that the producer is allowed to send data to the consumer. And the producer can send those 10 elements, send them like 1 by 1, but it may send them 1 by 1 or 5 by 5. It's up to the producer to send the data, okay? And the nice thing about this approach is that we can push this demand to the boundary of the system. So imagine, for example, that we have 3 processes here now. What is going to happen is that C, which is the sink, is going to ask for 10 events to B, and B is going to ask A. So we are getting this demand and pushing to the boundary of the system, because we probably want to get data from an external system, right? And then once A gets this data, we can send it downstream, right? So what does it mean, again, for GenStage to be demand-driven? So the first thing is that it pushes the back pressure to the boundary of the system, right? So if there's something in the middle that is slow, it doesn't matter. Or if it's the last step, it doesn't matter. We're going to push it to the boundary of the system. And internally, it's only messages between processes. It's a message contract, okay? And GenStage is just one implementation of this message contract. So for example, imagine that you're using GenStage and you don't like its API. You say, you know what, I'm going to do my own thing. You can do that. You can do that, and it's going to work fine with GenStage, right? Because it's only a message contract. And this demand-driven approach was highly inspired by Akka Streams. Huge thank you to Konrad Malawski from the Akka Streams team. He was really helpful. He provided a lot of feedback and gave a lot of interesting ideas. So let's see an example on how this all works, right? A very quick example. So imagine we have this very simple pipeline. We have a producer with a count, which means that it is counting 0, 1, 2, 3, up to infinity. And we have a printer, which prints the events that it receives, okay? To implement the producer, this is all you have to do. So you define a module called producer. You say you want to use GenStage. And then you're going to implement the init function. And this init function says, look, this is going to be a producer. And the initial state is the counter, like 0, right? And then you have to implement a handle demand function. And this handle demand function is called every time a consumer asks you for data, then we go and call the handle demand for you. So we're going to call the handle demand with the demand, which is how much data it was asked from you, and your current state, which in this case is a counter. And what we do is that we compute those events that we want to emit. So it works like this. So imagine, for example, that you start with the state with the counter of 0, and somebody says, hey, give me 10 events, right? So that function, handle demand, is going to return something like no reply, is going to return a list with 10 events from 0 to 9, and say, and now my state's 10. And now the next time somebody asks for 5 events, we are going to continue from where we stopped. We are going to emit 10, 11, 12, 13, 14, right? Then we'll update the state to 15, and so on, and so on. That's it. That's all you have to do to implement this very simple producer. And then the consumer is even simpler. What you do is that you say, hey, I want to define a consumer. It uses GenStage. I'm going to implement the init function. This init function says that I am a consumer, and I say that the state does not matter, so I just pass a random value. And instead of implementing handle demand, it has to implement handle events. And this implementation just sleeps for 1 second, prints all the events, and then moves forward. So after you wrote like these 20 lines of code all together, you just have to make all of it work. You just have to wire everything up, right? So to do that, the first thing that we do is that we start the producer with the counter of 0. So the initial state is going to be 0, okay? We start the consumer, which is going to be our printer. The initial state does not matter. And then we say, I want to subscribe printer, the consumer, to the counter, the producer. And after you do this, you are going to wait a second, and you're going to see the events 0, 1, 2, 3, up to 499, 500 events printed. And then you're going to wait another second. You're going to see more 500 events printed, and so on, and so on. Okay? So look, like we just had to write the code that gets the data, the code that processes the data. We didn't have to worry about anything else. We didn't have to worry about controlling how many events are sent. We didn't have to worry about controlling the demand. We didn't have to do anything else. Everything just works, right? But at this point, you may be wondering, but why 500 events, right? What is happening here that it chose exactly 500 events? And this actually comes from the subscribe option. So when you call subscribe, you can pass multiple options to configure that subscription. So one option is the max demand. The max demand is the amount of events, the maximum amount of events to ask for. So you can say, hey, give me at most 1,000. 1,000 is the default value. The second option is the minimum demand. And the minimum demand is the value that when reached, we ask for more events. By default, it's half of the maximum demand, right? And another option that we use a lot is the cancel option that tells how the consumer should behave when that subscription breaks, either because the producer terminated or because the producer canceled it, right? So you can say, hey, if the producer terminates, I want the consumer to terminate too, and that's the default, right? Just to drive this point home, let's take a very quick look on how this maximum demand and minimum demand work, okay? And why it's important to have those two parameters. So let's see what happens if the maximum demand is 10 and the minimum demand is 0. It's going to happen something like this. So the thing is that after the consumer subscribes to the consumer is going to ask for 10 items, right? And then the consumer will eventually receive 10 items. And then the consumer is going to process those 10 items, and then the consumer is going to ask for 10 more. And after the consumer asks for 10 more, because it has already processed everything, the consumer has to wait. This is not good, right? Which means that's basically like you are receiving a bunch of work, you are doing all of the work, and then you ask for more. Usually what you want to do is that you are doing some work, right? And when you see that, oh, I'm almost finishing, right? I already did like half of the work. I want to ask for more. And that's exactly what configuring the maximum demand and the minimum demand allows you to do. So if you say that, for example, the max demand is 10 and the minimum demand is 5, which is half, which is the default, the consumer is for 10 items. Sorry, the consumer is going to ask for 10 items. The consumer receives 10 items, and then because the consumer knows that the minimum demand is 5, okay, the consumer is going to process only 5 of those 10 items. So it's going to process only 5 of those 10 items because it knows that once it reaches 5, it can ask for more. So it's going to ask for 5 more, and then the consumer is going to process the remaining 5 while it waits for the producer to produce more. So in this scenario, if the producer is always producing items fast enough, right, the consumer never has to wait. The consumer is always working, okay? And that's it, and that's how it works behind the scene. There is one last feature from GenStage that I want to talk about, which is the idea of GenStage dispatcher. So right now we saw a very simple pipeline, right, that was unidirectional. And GenStage dispatchers is what allows us to change that. So what is a dispatcher? A dispatcher is something that is set per producer, and it is effectively what controls the demand and send data. So every time you receive the demand from a process and you want to send data to that process, the dispatcher regulates all of that. This is where the core of this logic is, and that's why you don't have to worry about it when you're writing your own producers and your own consumers. And the dispatchers enable concurrency because they allow us to dispatch to multiple stages, to multiple consumers. So, for example, the default dispatcher that we use is the demand dispatcher. And the demand dispatcher allows multiple consumers, right, to subscribe to the same producer, and the producer is going to choose which consumer it should send the data to based on the demand. So imagine, for example, that we have 5 events here, 1, 2, 3, 4, 5 to send, okay? And then we have 4 consumers. So you can think that at the beginning, the producer is going to send 1 event to each stage, right? But if the second consumer here, if the second stage, it's the one that processes its element faster, it's going to ask for another element earlier than all the others. So the 5th entry here goes to that one. So we're always trying to send the data to the process that is less busy, right? The one who asks first, because they're likely going through their data fast. But we have other dispatchers as well. We have, for example, something like a broadcast dispatcher, which sends the data to all the consumers. Or we have a partition dispatcher, which allows you to control to which stage, to which consumer the data goes to based on a partitioning function. Okay, so here we are using the reminder of 4, and then we can control which process gets each data. So one process is going to get 159, the other is going to get 2610, and so on. So we implemented all of this, and we announced this as a library. Some people started using it, and we announced this as a library in July 2016. And after we did that, a bunch of companies, they started using GenStage in production for a bunch of different use cases. So here are some examples. So Discord, they wrote a blog post on how they were handling bursts of over 1 million push requests per minute with the help of Elixir Creator. The folks at Adro, they did a redesign of their architecture for event processing. And at some point, they had a solution already in place, decided to use Flow, which is built on top of GenStage, and they were able to get further twice improvement over their throughput when they migrated to that as well. There's another case, for example, from the football edits folks, where they have to send a bunch of push notifications, which use HTTP2, and they use that with GenStage, and they were able to send 1.3 million notifications in just 10 seconds using HTTP2 and GenStage. Right, so, and these are just some examples. We have a bunch of other examples from the community, a bunch of other open source projects built on top of GenStage. And as we saw different teams, different companies using GenStage, it was clear that the majority of those users, they were using GenStage for data ingestion and data. So now you can see where this is leading, right? So, and what do we mean by data ingestion and data processing? So what were we seeing, right? So many companies using GenStage for concurrency back pressure, which is good. This is what it was designed for, right? And we saw a bunch of people building those data ingestion, data processing pipelines. And when they were doing that, we saw that they were implementing the same feature set over and over again. They were like, oh, we need rate limiting. We need batching. We need metrics, right? So we saw many companies, open source projects doing this kind of over and over. And not only that, we also saw some common difficulties, some common rules regarding complex pipelines when you had set up complex GenStage pipelines. And this is what I want to talk about. Like, I want to put ourselves like in this position where, oh, GenStage sounds great. I want to build a complex pipeline, processing pipeline at my work, and how that's going to work. Usually it goes like this, right? So usually it starts simple, right? Because that's how everything starts. So imagine that, okay, I need to build a data processing pipeline. So you create a supervisor and you say, for now I'm going to have only one producer, which is a process. And I'm going to have another consumer, which is another process, another. And those are children under the same supervisor. And you put this in production, it works, everything's perfect. And they're like, oh, this is great, it's working very well. I think now we can bump things up a little bit. So what I'm going to do is that I'm going to start 4 consumers, okay? So I have 1 producer and 4 consumers under the same pipeline. And this is the first mistake, okay? Because usually you're using the same supervisor, so what is going to happen here, the default supervision strategy is like 1 for 1. Like if a child terminates, only that child is restarted, right? So what would happen in this case, that if the producer terminates for some reason, if there's something wrong and the producer crashes, the default is that all the consumers, they're going to crash as well because they are linked by the subscription. So what would happen is that if the producer crashes, all the consumers, they would crash as well, and the supervisor would be like, oh my God, all my children are dying. And then it would say, and that would likely trigger a max restarts value in the supervisor, which would cause that supervisor to terminate, right? And potentially cascading the failure up. Eventually, the system would go back to a working place because that's why we have supervisors, right? But if you can avoid this failure, this cascading of failures, it would be good. So there are many ways to solve this. And the simplest way to solve this initial problem that you can say, okay, let's make the strategy, let's change it from 1 for 1 to rest for 1. And what this means is that if the producer crashes, it is expected by the supervisor that the consumers are going to crash as well. So the supervisor is not going to freak out. It has a slight downside, which is if a consumer in the middle crashes, the other consumers, they're going to crash too. But let's ignore this for now. This is good enough, right? Baby steps. So great. So you put it in production with the fix. It's working, and then you say, you know what? Now I think we can get like 2 producers because we can start to get even more data from the source. You're not maxing out the CPU yet, so let's inject more data into the system. So you change these to have like 2 producers and potentially multiple consumers. And now this rest for 1 strategy does not work anymore because you don't want if the first producer to crash, you don't want it to bring the other producer down, right? Those producers are unrelated. In fact, if one producer crashes, now you don't even want to like crash the other consumers anymore because those consumers, they can still be processing the data from the other producer. So you have to start re-engineering things again. So probably now what they're going to do is that they're going to say, look, I'm going now to have like 2 supervisors and a supervisor on top of that, right? So things start to get a little bit more complex. And usually if you have multiple steps in your pipeline, you have even more supervisors and processors here in the middle. Sure, you can set all this up, right? It's just a lot of work, like it's a lot of repetition that you have to do. And even if you solve those problems, there is still one problem here, which is how you're going to do a graceful shutdown of this system, of this tree. Because in Elixir and ERLANG, when you tell the system to shut down, what it does is that it goes through all the supervision trees and say, hey, supervision tree, please shut down, right? And then the supervision tree shuts down by terminating the children in the opposite order that they are started. So here we start first the producer because we want the consumers to subscribe to them, right? So we start things producer, producer, and then the steps in the middle and the consumer, which means that when we're going to shut this down, the first thing that we are going to terminate is the consumer, right? And this is horrible, right? Because imagine that you have a bunch of steps and you terminate the consumer. All the data that is here in the middle, it's never going to be concluded, right? It's never going to get to the end because the consumer is the first one you terminate. So usually what you do is that you go in and set terminator T3000 process, and the whole role of this process here is to just wait until the supervisor says, I'm going to shut things down. So this process would say, all right, I can see that you want to shut things down. Wait just a second. what I'm going to do is that I'm going to flush this pipeline, right? So I'm going to go to the producers and say, hey, producers, you should stop listening to demand now. If people ask you for more events, don't fetch more events. Stop doing that. And flush everything you have. And then the producers flush and tell the terminator, hey, we flushed. And now the terminator go to the steps in the middle, do the same thing, and then eventually you're going to get to the consumers and say, hey, consumers, please flush. And then let me know when you're done flushing, because I'm going to tell the supervisor that it can now proceed to terminate the pipeline because we have flushed everything, right? So when we're talking about complex GenStage pipelines, there are a bunch of questions that we have to answer. How to structure supervision trees correctly? How to handle graceful shutdowns without data loss? How to reduce the amount of events lost during failures, right? And but one thing that I also want to highlight is that if you're running GenStage in production today and you haven't asked those questions, there is no reason to panic, right? Because usually when you're getting data from those external systems, it has things like dead letter queues. A good and well-designed pipeline is idempotent. So if you have to repeat something, that's not going to change the end result of the system, right? So usually we have other ways to cope with data loss, right? And those systems, they're actually in place. But if you do think about this, and at some moment you're discussing with your team about doing the optimal pipeline design, you are going to come through those questions. And you have to spend like brain cycles answering those questions. And it was exactly in this context that Broadway came to life. So now to do a very quick recap on Broadway on the features it provides. Okay, so Broadway is a new library for concurrent and multi-stage data ingestion and data processing with Elixir. And why is it called Broadway? It's because we have multiple stages, multiple producers. It's a pun on the stage and producers thing, right? So what does Broadway gives us at the end of the day, right? So back pressure and concurrency, right? It comes just because you're using GenStage. We get that for free from using GenStage. It also gives us automatic acknowledgement. So if you're using SQS, you don't have to go and write the acknowledgement by hand. When you say, I'm using the SQS producer, the producer sets up everything, the acknowledgements for you. Don't have to worry about it. It gets fault tolerance with minimal data loss. So we take care, like, if the producer crashes, we're not going to bring the rest of the tree down. We can manage those failures. So we take care of all this for you. We already took all the decisions, hopefully the correct ones. And we provide graceful shutdown. So the terminator process there that we were talking about, it's implemented. It's there. It's part of Broadway. And you also get batching and partitioning. So we're talking about the batching, right? Oh, we need to batch the events before I acknowledge them. We do that for you. You just have to configure. You just need to let us know to do that. And partitioning works similarly. And again, to leverage all of these, you just have to write this code, right? You just have to say, I'm using Broadway. You implement the pipeline, right? You implement your handle message and handle batch callbacks, and everything is done for you. That whole supervision tree, right, that we were talking about, we are going to set it up for you. You don't have to worry about it. So that's it. That's Broadway. I hope you have enjoyed the talk and the purpose behind it. And if you have a use case for Broadway, I would love to hear about it. I would love if you could try it out. So how can you help, right? If you want to get involved. So the first thing that you can do is to give the version 0.1 a try. So again, like beta warning, right? We literally released it like 2 days ago. 3 days ago, thank you. And, and you can also write a Broadway producer for our favorite thing. So like, oh, I want to get data out, I don't know, whatever, of the system. Okay, you can write a Broadway producer for that. Right now, we have only Broadway SQS. We are working on the RabbitMQ1. I'm going to talk about it soon. But if you have a current GenStage pipeline with your own GenStage producers and you want to use Broadway, you don't have to worry because you can also plug GenStage producer that you want inside Broadway. We have guide documentation. We are really proud of writing a lot of documentation, so we hope the documentation that we are going to find for Broadway is really, really good. But if it's not, let us know, and we'll improve that, right? But you can plug in GenStage producer as well, okay? So what are the next steps for us, right? So we want to allow batchless pipelines. So today you have to do batching, but some tools may not require that. So for example, it's not required by RabbitMQ. It's not required by Amazon SQS as well, but unless you want to throw money at Amazon, you're usually doing batching. We also want to provide built-in metrics and statistics, so you have like great coming out of the system. You have great data coming out of the system without having to do extra work. We want to do automatic backups and a couple other things. And finally, I want to thank my company, Plataformatec. For those who don't know us, we are a consulting and software engineering company, and we are the company behind Elixir. Elixir was born as a research and development project inside Plataformatec. And Broadway is yet another research and development project coming from Plataformatec. And it's one of the many projects that we have. And we hope you enjoy it. And that's it. I'm right on time, so I believe I won't have time for questions, but I'll stay around and I would love to talk. Thank you very much.